Buddy? So regression with categorical predictors, we already covered this, and we said we use dummy variables. If we have two levels, we only need, if the categorical basically variable has two levels, we only need one dummy variable. 0 represents one level and 1 represents another level. If we have three levels, we need two dummy variables, and let's say level 1, level 2, level 3. Then for the first dummy variable, we have 0. For the second one, 0. And this is for the second and the third one. Then we can basically construct our design matrix based on these zeros and ones, and we can find basically, use the same equation, x transpose x inverse, x transpose y, to find our estimates for beta. Okay, that's basically easy. Question, there were like lots of questions. Can we use other numbers, 1, 2, 3, or can we use basically the quadratic form? I think you can do, but you need to be careful for in terms of interpretation. Okay, so it's not going to be that easy to interpret compared to 1 and zeros. Okay. And what if we have basically y as a Bernoulli variable? So what if we have y as a categorical with two levels, which is 0 and 1? And you know that's the distribution of Bernoulli variable. And we have some x's, and we want to find a relationship between y and x's. Okay? Your y is binary, 0 and 1, which follows a, let's say, Bernoulli distribution. This is the PMF for Bernoulli distribution. If you remember, the expected value is p, the variance is p times 1 minus p. What we want to do, we want to find a regression model, y against x. So these are the y's that we have. They are either 0 or 1s. So this is basically sort of scatter plot, okay, y versus x. So this is x, and this is y, which is either 0 or 1. So as you can see, linear correlation or linear relationship, no way. Okay? But we can find some nonlinear function which explains this. So for example, this S-shaped function starts from here and then goes up to here. So that basically can capture lots of variation. So if you use so that S-shaped function is a good approximate for explaining. But if you want to use one line, it doesn't explain anything. Yes? Actually, it's continuous with respect to x. But your y, the one that you observe, is basically discrete. It's 0 and 1. So your x's is continuous, as you can see. Okay? But your y is either 0 or 1. So let's say you have some features. Okay? You want to predict whether something happens or not. Okay? So one example would be you have some test results from like medical test results, and you want to see if the patient has a cancer or not. Okay? So your response variable is 0, 1. But the features could be either continuous or discrete. In this case, we are considering this is continuous. Does it make sense? Yeah. But y is definitely discrete. X could be either in that setting. So 30. So what's happened here, for example, if this is your prediction model, 30, you go up, so it's somewhere in between, so you don't know whether it's exactly. So at the end of the day, what we are going to predict is the probability, not exactly 0 and 1. And you define a threshold on that probability. If it is less than this threshold, you say this is 0. If it is greater than threshold, you say it's 1. Yeah. Okay, so what we are going to do, we want to predict this y using this basically S-shaped function, and this is that S-shaped function, okay, which we call it logit function, okay. Any questions so far? Now, do you remember in regression what we do? We are trying to estimate expected value of y given x. Okay, in the linear regression, the expected value of y given x was beta 0 plus beta 1x. That's for linear regression. So what is the expected value of y given x? We know that for Bernoulli, expected value of y is p. Okay, if I go to the previous slide, expected value of y is p. But this p is not constant. This p is probability of success. You remember probability of observing 1. So this p is not constant. It's a function of x. So probability of observing 1 success is a function of some variables. Does it make sense? So probability of a patient having a cancer is a function of their test results. Does it make sense? So your expected value of y given x, which is p, and it's function of x. And this function is defined by that logit function, as you can see. So probability of observing a success is defined by this function. So actually what we are trying to estimate is this guy. All right? So we are trying to estimate those parameters. So what we are estimating at the end of the day is not y, is probability of success. Because y is 0 and 1. That's the input data that we have. But what we are estimating is probability of observing a 1. Okay? So probability of observing a success. Probability of when I do this experiment, I get a 1. That probability is between 0 and 1. Okay? So your p of x would be between 0 and 1. And if you want to translate it to, let's say, 0 or 1, then you define a threshold. For example, one simple threshold is what? Is 0.5. If it is less than 0.5, you say this is 0. I'm sorry. If px is greater than 12.5, you say this is 1. Does it make sense? Okay. Yeah, question? No. Okay. Any questions here? So is it clear what we are trying to do? We want to do basically regression for binary output, but at the end of the day, we get the probability of observing 1, probability of observing 0. Then we can define a threshold to say it is 1 or 0. Now, how we can do that? We can use MLE for that. Remember, this is probability mass function, p to the power of y, 1 minus p to the power of 1 minus y. Okay? So I have a set of data, y and x's, 1, 0, 0, 1, and I have corresponding x, 20, 30, 40, 10, and blah, blah, blah. Okay? So I have this pair of data. I want to use this data for estimating our beta 0 and beta 1. Okay, this is basically the PMF function. I can define the likelihood function. But the likelihood is a function of x. So your p is not p anymore. It's p of xi. This is not multiplication. This is a function. P is a function of xi. To the power of y, 1 minus p. Actually, there is one parenthesis missing here. 1 minus pxi to the power of 1 minus yi. How many observations do I have? N observations. And I assume that those n observations are independent. Therefore, this is going to be my likelihood function. Do you remember the definition of likelihood function? That's the same thing. Now I replace p with this guy. So, and do some simplification at the end of the day. That is the likelihood log likelihood function. Actually, if you take a log, you can get rid of exponential function part here. And at the end of the day, that's what you get. Okay? So how I can optimize? You remember you take a derivative and you try to calculate a score function and stuff like that. Here there is no closed form solution for it. So if you take a derivative, you set it equal to 0, then you want to try it, to solve it, there is no closed form solution. So what you do, you basically use numerical method to solve that equation. Okay? And I don't go through the details, but there is an algorithm which is very popular for solving that likelihood function or optimizing this likelihood function called IRWS, iterative recursive weighted least square. So yeah, that's IRWS, and then if you use like a software, it can easily solve that for you. One example, let's say we want to find a relationship between the failure of something called O-ring, and it's maybe aerospace people know what this is, as a function of temperature, as you can see. So we have different like pair of variables, different temperatures, and O-ring failure, if it fails or not at different temperatures. We want to find the relationship between these two. And this is the scatter plot. So that's basically the temperature that you have. This is for zeros, and this is for ones. And this is the function that we are estimating at the end of the day. So this is the output of the software. You have the coefficient beta 0. So that's beta 0 hat. That's the standard deviation of the coefficient. That's the test. And it says maybe intercept is not significant. You can see because p-value is not less than 0.05. How about the temperature effect? Temperature effect, yes, it's significant. It's less than 0.05. And there is a negative relationship between temperature. I mean, the coefficient is negative. Okay? So what does it mean? It means when we are increasing your temperature, that the probability of observing a failure decreases. Okay? Does it make sense? For higher temperature, we have less probability of observing a failure. So basically, here, this is what we have. It's negative 10.87 minus, she is positive, sorry, minus 0.171x. That's the function that we are estimating. Any questions? Yes.
What are Z, P, and the odds ratios?
So Z is the Z-test. If you want to do Z-test, you remember we did T-test. P is the P-value corresponding to that Z-test. So that's why I said, so this basically for the hypothesis testing, whether this coefficient is equal to 0 or not. Okay? So that's the P-value corresponding to that hypothesis test. So we cannot reject H null, which means, yeah, there is no basically intercept. We can get rid of the intercept. How about this guy? This is the Z-value corresponding to beta 1, and this is the P-value corresponding to that hypothesis test. It says it's significant, and the effect is because it's less than 0.05, and the effective is negative. Okay? So when temperature increases, the probability drops. When temperature increases, the probability of failure drops. Okay? Lower and upper confidence interval for the temperature, and you have odds ratio. Okay, what is odds ratio? Yeah, so I want to see what type of odds ratio here this guy is talking about. Odds ratio, I don't know. I need to look it up. Because odds ratio usually has like the ratio of odds, two different odds. Odds means basically if you have theta 1, or let's say P1. It's P1 minus 1 P1. And then if you have another P2, like another parameter, P2 is P2 divided 1 minus P2, and this is odds ratio. But I don't know exactly what this odds ratio is in that output. I don't know. Anyways, any questions? So this is basically goodness of fit test to see whether basically test whether all slopes are 0 or not. And as you can see, p-value is 0.015. This is similar to that ANOVA test. Do you remember? Beta 1 is beta equal to beta 2 equal to beta 3 up to beta p. All of them are 0 or not, basically. Okay. Any questions? This is not going to be on the exam. Just to remind you. Okay, let me start new topic, which is goodness of fit. So goodness of fit and contingency tables. So basically, so far we assume that this random variable or this sample follows a normal distribution. And problem gives you this one follows a Poisson distribution. This one follows a geometric distribution. But in reality, if you have a set of data, how you can test whether it's coming from a Poisson distribution, normal distribution, or geometric distribution? So goodness of fit test, the main purpose is to basically test the hypothesis about the distribution. Okay? And so let's say, for example, in this data, we have a sample of 60 basically printed boards. And what we do, we count the number of defects on each board. Okay? So what happens is this. So this is basically board number 1, number of defects, let's say is 2. Board number 2 is 0. Board number 3 is 1. Board number 4 is 0. Board number 5 is 1, 6, and so on and so forth. Okay? So we inspect 60, and we want to see if the number of defects follows a Poisson distribution or not. Does it make sense? The problem setting? So, because we know that usually number of defects in a unit or number of events in a unit follows a Poisson distribution. So, number of events, which is defect, in a unit, which is one board. Okay? So how we do that? As I said before, H null is the probability distribution of the defect is Poisson. H alternative is the probability distribution of defect is not Poisson. Okay? We first summarize what we have. So we see how many zeros, how many boards do we have with 0 defect? 32. How many boards do we have with 1 defect? 15. How many with 2? 9. And how many with 3 is 4. So we kind of like summarize and find the observed frequency. So the procedure that we do, basically we follow in a goodness of fit is as follows. We calculate, okay, the expected probability. We calculate the actual probability. If these two are close to each other, we said it follows Poisson distribution. So what I mean by that, for number of defects, so let's say X is number of defects. It's 0, 1, 2, 3. It could be any numbers. Because Poisson distribution starts from 0 up to infinity. Then what I do, I'll calculate actual probability, or let's say, expected probability, and yes, observed probability. Okay? So expected probability and observed probability. How can I calculate observed probability? That's easy. Why? Because I know out of 60, 32 are with no defects. So what is that probability? 32 divided by 60. So I can easily find observed probabilities. How about expected? For expected probability, I can find probability of x equal to 0, for example, and use, so let's call it I, use Poisson PDF or PMF to find basically the expected probability. Then I compare these two numbers. If they are close, probably it's coming from a Poisson distribution. If they are far, it's not coming from a Poisson distribution. That's the concept behind that. Okay? So what we do, we try to find the difference or deviation from basically expected, and then set up a hypothesis test based on that. So that observed is this guy. This is OI, and this is expected, EI. So as you can see, OI minus expected squared divided by EI. So it's kind of like a standardization. And under a null, if it actually follows a Poisson distribution, I expect this guy to be very small, because there should be not large differences between observed and expected. So under a null, this guy follows a chi-square distribution. And I don't derive the details here, but if you are interested, this is pretty old. You can see that paper from 1900. Yeah. They show that this follows a chi-square distribution. Okay? Anyways, so this is the procedure. So as I said, OI is the observed frequency in the ith class interval. E is the expected frequency in row I. First, we need to calculate the probability of each interval and then find the expected frequency. So let me do it here for this data. Do I have it here? Yes. Okay. So number of defects, x is either 0, 1, 2, 3, or more. So as I said, your Poisson distribution is 0, 1, 2, 3, 4, up to infinity. Okay? So I continue up until I don't observe any other defects. So here in this case, we don't have the observed frequency for 4 defects is 0. So just say 0, 1, 2, 3 or more. Okay? So let's see. What is the probability associated with that? For 0, probability of x equal to 0, I'm going to use this one. But the question is, what is lambda? So I is 0. I want to find probability of x equal to 0, which is... But what is lambda? What? How?
Guess a bunch.
You can estimate it.
Yeah, exactly. We can estimate it. What is the best estimator for lambda? Is x bar. Okay? So just find x bar. So what is the x bar for this guy? Our x bar is 32 of them are 0. 15 of them are 1. 9 of them are 2. And 4 of them are 3. Divided by 60. Okay? And if you do that, it would be 0.75. So basically what I'm doing is I'm just adding up the number of defects divided by 60. Okay? So px0 is e to the power of minus 0.75. By the way, this is on the exam. Okay? Just want to make sure you know that. x1 is 1 factorial 75 0.75 to the power of 1 factorial. This is 0.354, and I don't calculate the rest except for the last one. So last one is greater than equal because I said 3 or more. Okay? So this would be, let me write it here, probability of x greater than equal 3. It's a summation of I from 3 to infinity, e to the power of minus lambda. In this case, is 0.75. 0.75 to the power of I factorial. And this would be 0.041. How we can calculate this summation? Do you remember it? No? 1 minus the others. Yeah. So this one is 1 minus P0, P1, P2. Or, so this is P0, P1, P2, then you calculate. So these probabilities are 0.472, 0.354, 0.133, and 0.041. Then I get expected frequency. So expected frequency, how many observations do I have? N. What is the probability? Pi. So expectation is N times Pi. In this case is 60 times, so basically N times Pi. 60 times 0.472, which is 28.32. 21.24, 7.98, and 2.46. Is it clear? Any questions so far? You good? So that's for expected. Then we have observed. Observed is oh, it's up there. 32, 15, 9, and 4. Okay, how many boards do have like 32 defects? I'm sorry, how many boards do they have like 0 defects? It's 32. How many boards? 15. I'm sorry, 1, 15. How many boards? 2, 9. 3 or more? 4. Okay? Any questions? You can do that, but that test is based on the frequency, not the probabilities. So if you want to use like chi-square distribution, then you need to do the frequencies, not probabilities. Okay? You can do that. It's basically, you don't change it, but you need to make sure instead of here, you need to divide it by. So it's basically here. You are dividing everything by n. Okay? So yes, it's simpler, but if you use probability, it's not going to be exactly the same as well, because in numerator you have a squared, in denominator you have just order 1. So if you divide it by n, both numerator and denominator, you are not going to get the same thing. Do you know what I mean? So if you want to change this to probability, you need to divide it by n. Is that correct? So, but numerator is a squared, denominator is order 1. So it's not going to give you exact chi-square. So the chi-square, exact chi-square, or approximate chi-square is based on your expected frequency rather than expected probabilities. Okay? Any questions? Are we good here? Okay. Now, so what should we do? We calculate this quantity and we compare it with chi-square alpha k minus p minus 1 degrees of freedom. Okay? K minus p minus 1 degrees of freedom. So k is the number of intervals that we have. P is the number of estimated parameters. Okay? That makes sense. You remember, for example, n minus p was the degrees of freedom in regression because we are estimating like p parameters. But why do we have minus 1? Anybody can tell me? N minus p makes sense, but why n minus p minus 1? Yes, we do, yeah.
Not 2, then it's 3. So you don't have that extra degree of freedom.
No, why that 1?
Because the probability sum to 1.
Exactly. Because the summation of probabilities sums to 1. Okay? So, for example, this one, this one, this one, you know, but not this one. This one, this one, this one, you need to estimate, but not this one. Why? Because the summation of these probabilities is going to give you the last one. That's why you have 1 degrees of freedom difference. Anyways, so you compare it with that threshold. If it is greater than the threshold, H null is rejected. Otherwise, H null is not rejected. So there is one exception. The exception is as follows. Let me see if I have it somewhere here. Yes. If the expected frequency for an interval is less than 3, the interval should be combined with the previous interval. Okay? So let's look at what we have here. The expected frequency is 28, that's fine. 21 is fine. 7 is fine. Here is 2.46. So it's less than 3. So we need to combine this interval with the previous interval. Okay? Does it make sense? So if we do combine them, then what's going to happen? I have 13 here, and I have, what is this number? $10.44. Now, I need to find chi-square 0, which is summation of I from 1 to k, which is the number of intervals. Expected, observed minus expected squared divided by expected. In this case is 28.32. The other way around. Doesn't really matter, but square divided by 28.32 plus the second interval, 15, observed minus expected, square divided by 21.24. And the last one is 13, which is the after combining the rows. 10.44 divided by 10.44. This is 2.94, which should be compared with chi-square of 0.05. K is the number of intervals after you combine them. Okay? So now the number of intervals is what? Is 3 minus P. The number of parameters that you're estimating, how many parameters you're estimating? For Poisson, you're estimating just one parameter minus 1, which is 1. And that is 3.84. This is less than, so don't reject H null, which means the assumption of Poisson distribution is not a bad assumption. Okay? Again, this 3 is K minus P minus 1. K, P, 1. K is the number of intervals. After combining them, P is the number of parameters. And question. Yeah. So you mean by changing this, for example, if we reject H null when we are using MLE, then if you change it to something else, maybe this cannot. I think for the distributions that we know, most of distributions that we know, the MLE and MOM estimator have the same form. For example, if you use method of moment for that, and MLE is the same. But what you are saying, I would say, that combination is because the assumption of chi-square distribution, okay, is only valid if you have at least some, some basically expected frequency in one cell. If you don't have that expected, then chi-square distribution is not going to be a good assumption. That's why they combine it. Yeah, the details is given in that like old paper, but that's the concept behind that. Yeah.
Okay. We take out the -1 from the chi-square because we're not estimating.
Oh, the question is, what if the lambda is given? The lambda is given, first of all, you need to recalculate everything here. Okay, that's the first step. The lambda is given and you are not estimating, you remove, you recalculate this based on not 0.75, based on 2. Then when you are comparing, this would be K minus 1, not K minus P minus 1. Yes, because the parameters are already given. For example, for normal distribution, if one is given, the other one is not given, then you use P. For example, if mu is given or sigma is not given, you use P equal to 1. Yeah. Yes.
Have the like k minus p minus 1 because you still have the rest of the probability equal to the first three, even if you know lambda?
No, that's okay. That 1 is taking care of that. I'm talking about P.
Oh, okay.
P is the number of parameters that you're estimating. So you're not estimating. Yeah. Question?
Can you go over one more time why the intervals are combined?
Oh, that's the rule basically that we have. If the expected frequency, so we already have it here. If the expected frequency for an interval is less than 3, this interval is less than 3. It's 2.46. We combine it with the previous interval. The expected frequency, not observed. Okay? And the reason is that chi-square distribution on the rational is not going to be chi-square if we have a table, like a row with expected frequency less than 3. That's why we combined it with the previous one. You need to make sure that this is one of the conditions that they have. Any other questions? Good? Okay, one example for basically, I don't have time to go over this example, but what I'm going to do, I'm going to either solve it on Wednesday or post the solution on T-square. So this is for geometric distribution. You need to do the same thing, basically your expected value instead of, the expected frequency, that P, instead of using Poisson distribution, you just use geometric distribution. That's it. Okay? And then your chi-square k minus p, again, p is the parameter, number of parameters that you're estimating, and this parameter is this guy. So the only tricky thing is how to calculate p, which is the probability of success. I mean, it's not tricky, it's very straightforward, actually, which is the number of success divided by total number of sample that you have. Okay. Normality test. So what if we want to basically use it for normality, normal distribution? So for normal distribution, what we need to do, do you remember for Poisson, we had different rows and different intervals? And intervals are basically, it's very intuitive. Okay? But for normal distribution, we have continuous number. So what we need to do, we need to define some intervals. Okay? That's first of all. So here, again, the null is the probability of distribution is, this is not defect. This is basically there's a length of part. Is normal, and H alternative, the distribution is not normal. So what we do, we find the range. Okay? The range of data that we have is, let's say, is from 4.948. This is the minimum, and this is the maximum. And we divide this range into equal intervals. Okay? How many intervals in this example? 1, 2, 3, 4, 5, 6, 7, 8. The smaller one should cover from negative infinity to this number, and the largest one should be from this number to positive infinity. We need to find observed frequency. This is from the data that we have. So we see how many data points we have less than this number. So actually, this is not minimum. Minimum is somewhere less than this. So how many parts, let's say, have length less than 4.9? 12 of them. How many between these two numbers? 14 of them. How many between these two numbers? 12. How many parts we have inspected? 100. How about the expected frequencies? Okay. So as you can see, these expected frequencies are the same. So what does it mean? Actually, the intervals don't have the same length, but they have the same probability. Is it necessary to do that? No. You can have the same length, not same probabilities. But the way that you calculate expected frequency, so expected frequency for each row is n times pi. Your pi is probability of x between Li and Ui, where Li is the lower bound and Ui is upper bound. So let's say probability of interval 3 is probability of x between for interval 3, 4.986, yes, and 5.014. We want to find this probability. So we need to standardize it. So we need to subtract mu divided by standard deviation. Now the question is, what is mu and what is standard deviation? We estimate mu with x bar. In this case is this guy. And we estimate sigma with s. In this case is 0.08. Okay? So this gives me z. Okay? And this is 4.986 minus 5.04 divided by standard deviation. And 5.014 minus 5.04 divided by standard deviation. So you can easily find these two, which is from table, you can find these two numbers, and it's going to be phi of, let's call this B, let's call this A, so it's phi of B minus phi of A. And that number is P3, and your E3 is N, which is 100 times P3 which is 0.125. This is 12.5. Okay? These are the expected. Yeah, actually, that's true. But, like, I mean, it's not exactly Z, but yes. The thing is, we are approximating T distribution with Z distribution. We are assuming, this is, again, it's not going to be Z also. But we are assuming mu, x bar is mu, and sigma, S is sigma. That's the assumption. Sort of like approximation. You're right, because we are not using basically mu here, and it's not exactly T either. Why? Because for T it should be x minus mu divided by S, not x minus x bar divided by S. Remember? X minus mu divided by S gives you a T distribution, or x bar minus mu to be exact. But I'm saying x minus x bar. So it's kind of like a crude approximation. I'm just replacing mu with x bar and sigma with basically S. Okay? So one thing is, all expected frequencies are 1, which means actually intervals are not, intervals do not have equal length, but they have equal probabilities. So that's the first interval, which is this probability, second interval, the third interval, probably fourth interval, something like that. So these probabilities are the same. All of them are 0.125, 0.125, and so on and so forth. Is it necessary to do this way? No. Okay, you can have different length if you want. Now, what should we do? We need to calculate chi-square, which is observed minus expected square divided by expected, and this is 0.64. This is very small. So definitely, normality test is not, will not be rejected. We need to compare it with this guy, And like how many intervals do we have? In this case, is it 8? Yeah. 8 minus p. What is p? 2, because we are estimating both mu and sigma, minus 1. So it's 5. You find it and you compare this number 0.64 with that. It's less than this. We do not reject H null. Okay? Any questions? Yes.
5B and 5A.
I'm sorry? Oh, what are those?
Yes.
So this is a number. I call it B. This is a number. I called it A. Phi of B is the number that you get from the Z chart, which is the CDF of B. From the Z chart, like a Z table, that's phi of B. A number that you get from the Z table for A, which is the CDF of standard normal, this is phi of A. You subtract them, you get the P, which is 1. Yeah. Any questions? Okay. I'll see you on Wednesday. And Wednesday you have a homework due. Also, we will have a Q&A session. Okay, I'm going to go over the practice exam. I'm going to give you some more information about the exam, how long the exam would be. But don't worry, the exam is not going to be as long as the practice exam. I just wanted to give you more questions to practice with. One thing else is we posted 2 set of examples, more examples on confidence intervals and hypothesis tests. Another one for ANOVA and regression. Okay, there's a folder on basically TS2 called, I think, more examples, something like that. Okay, any questions? See you on Wednesday.